All right, this is our last video for Kinetics. I bet you are super stoked. I'm stoked too, because I don't have to sit up in my office by myself and not be able to watch American Horror Story. Instead, I'm making these videos, but just because I love you guys, okay? So I'll shut up, get into the notes. First, we are going to talk about, in this video, catalysts. So you already know what a catalyst is, how we pick a catalyst out from our reaction mechanisms. Now we're going to talk about specific types of catalysts. The next thing we're going to talk about, very short and sweet, how to calculate activation energy. We've been talking about activation energy ever since thermochem, but how in the world can we calculate it? Okay, so those are the two things we're going to focus on for this video. Now, starting with a catalyst, we know that a catalyst is, it starts as a reactant in a reaction mechanism in our elementary step, and then it is brought back. It's produced at the very end because it's not consumed at the very end of the reaction mechanism for the last elementary step. Sometimes catalyst can be included in your rate laws. And so that's a little disclaimer that I'm going to talk about in just a second. But otherwise, we cross out our catalysts. They're not included in our rate laws. So the definition of a catalyst is what it does is it lowers activation energy by providing an alternate pathway. And I believe we've already talked about this before when we were talking about how catalysts can affect reaction rates. We know because these catalysts lower the activation energy by providing an alternate pathway, that it actually makes the reaction happen faster. So what I want to look at here is just make sure we make the connection. If I want to draw an exothermic graph, for instance, so we have an exothermic graph where my products are ending lower than my reactants energy. If I have a catalyzed reaction, I'm going to draw this in a dotted orange line. My catalyzed reaction is going to start at the same energy as my reactants. It's going to end at the same energy as my products, but it is going to lower the activation energy. So you see now my activation energy had to go to the peak up here. Now my activation energy only has to go to the peak there. So it's providing a shortcut in order to make the reaction take place. So the only thing that a catalyst alters is my activation energy. If you remember from thermochem, we have delta H, which would be products from reactants. It would be the difference there. You see how it doesn't affect delta H. It doesn't have anything to do with delta G. The only thing that a catalyst does is lower activation energy. And it does that by providing an alternate pathway. So we have a couple of different types of catalysts. One is known as a homogeneous catalyst, heterogeneous catalyst, and acid-base catalyst. A homogeneous catalyst, all that is that the catalyst is the same state of matter as my reactants. So say, for instance, we have some reactants that are gases, right? So a gas plus another gas. If I add a catalyst there that is also a gas, that would be titled a homogeneous catalyst. This is the case scenario where you can have the homogeneous catalyst included in my rate laws. So can have homogeneous catalyst in rate laws, but this is the only time when that's the case. The reason why is because since it's the same state of matter, it could actually alter the rate law. Okay, so if you see that there's a catalyst in a rate law from the mechanism, but it doesn't look like it should be because it's a catalyst, then more than likely it's a homogeneous catalyst. And I think there's an example we'll do in our free response problems later on. So this will make a connection for you guys. So homogeneous catalyst. The next is a heterogeneous catalyst. A heterogeneous catalyst is when the state of the matter of the catalyst is different from the state of matter of my reactants. So let's say again, we have both of those gases reacting there. Well, I introduce maybe a liquid catalyst. So this would be an example of a heterogeneous catalyst. An acid-base catalyst is when I take an acid or a base and introduce it into my reactants. So if I add an acid catalyst to this, then that would be an acid catalyst. If I were to take a base catalyst and add it to this, then it would be a base catalyst. Now, I normally do these demonstrations in class, and I still would like to do these demonstrations for you, but I just want to show you some examples on the internet, and then one day in class, we'll take some time and we'll actually do these demonstrations as well, because they're quite fun. So what I have for you at the very beginning is a homogeneous catalyst. So I'm just going to kind of scroll through and show you what's happening here. So in this flask, you have hydrogen peroxide, which is a liquid. And what you're doing is, well, hold on. All right, you're adding food coloring and dish soap. And then you're adding potassium iodide. So I want to pause it right there. Do you see how the potassium iodide was also a liquid? So that means since my reactant was a liquid, the hydrogen peroxide, and since the potassium iodide was also a liquid, the potassium iodide is a homogeneous catalyst. And so here's what happens. This is called the elephant toothpaste reaction. It's quite fun. I'll back it up so you can see it really well. And boom. It's really cool. Now, this reaction is extremely exothermic. It gets really hot. And so when we do this in class, you'll be able to see how hot it actually gets and things like that. Ooh, there's some more elephant toothpaste, okay? So that's pretty cool. So the catalyst there is potassium iodide. It's homogeneous because it's the same state of matter. So the next one that I want to show you is the Genie in the bottle. So this is also hydrogen peroxide that this scientist is putting inside the bottle. And the catalyst that they're adding here, let me see if I can scroll forward. The catalyst that they're adding is solid manganese dioxide. So there's a solid in there that he's going to take out any moment now. Okay, poor dude. There you go. You see that solid? So he's going to put it in the, sooner or later, there we go. He's going to put it in here, and you're going to have a reaction. So it looks like a Genie bottle, and it's pretty cool too. So I will also do this demonstration one day in class for you guys. Just remind me. So that is a catalyzed reaction there as well. What's happening is hydrogen peroxide is being broken down into oxygen gas and water. And it takes a very long time for hydrogen peroxide to do that. So this is the reaction for both the elephant toothpaste and the Genie in the bottle. So it's just the hydrogen peroxide being broken down to oxygen plus water. Now, it is an exothermic reaction, so it releases a lot of energy. And so the vapor that you see there is, since it's extremely hot, it's exothermic, that water is actually vaporizing to turn into the gas form. And so that's what you see there. You see bubbles because that's the oxygen gas as well that's being produced there. Well, the manganese dioxide that's solid, it's a heterogeneous catalyst. It is what is causing the reaction to happen faster. On the other one, it was potassium iodide that was the catalyst there. So the last type of catalyst that I want to show you, this one is a sulfuric acid catalyst. So it's an acid catalyst. So what they're doing is they're putting sugar in this beaker. And then they're adding sulfuric acid. So this has to be really highly concentrated sulfuric acid for it to happen. So we have an acid catalyst being added to just sugar. There's nothing else in it, just sugar. And let's see what happens. I'm going to fast forward this a little bit. And so what we actually see happening is this really cool reaction where all it is the sugar being broken down to make carbon. So this black stuff that you see being produced here is a basically carbon, graphite, what you see on the thing. It also is extremely exothermic. So what we probably have being produced in addition to that is some water that's being vaporized, maybe some carbon dioxide gas, and different things like that. So they call this, I think, like the carbon snake reaction, I think. But it's really cool because all it is sugar with some acid, sulfuric acid added to that. So it's pretty cool. And again, I'll show you these demonstrations. Just remind me to show it to you in class. So let's go back to our notes. We've talked about catalysts. That's really all you need to know about those. Remember that a homogeneous catalyst could potentially be used in my rate law expressions. So just be aware of that. The last thing that I want to talk about is how to calculate activation energy. So I'm going to clear me some space on here. So activation energy, we've talked about like how to figure out if something's higher than the other and all that good stuff. But how in the world do we actually calculate it? Well, activation energy, I'm going to say that it's E sub A. It has to be experimentally determined. Don't you love my handwriting here? Boom. That says experimentally determined in case you can't decipher it. All right. So here's what you have to do in order to solve for activation energy. The very first thing you have to do, design an experiment. So you are going to collect some data. And the data that you're going to collect is temperature versus rate constant data. Remember, rate constant is the lowercase k. Okay, so I can do temperature and rate constant. I know that I had a lot of, especially my double period kids, if you're watching this video, a lot of you guys said, well, I've been given temperature on my questions for differential rate law when it's asking for me to find K. Does that matter? No, the only time when it matters is when I'm changing my temperature. If I change my temperature, my K value changes because K is temperature dependent. That's the only time when K changes for a particular reaction. Okay, so just make sure you know that those two correlate. Once I collect this data, I conduct an experiment, I do find different temperatures, figure out different K values. I am then going to plot that data. And on my y-axis, I want natural log of K. On my x-axis, I want 1 over temperature. Realize this is temperature, not time. So 1 over temperature. And when I plot that data, I'm going to get a straight line that's a negative slope. This slope is very important because this slope is equal to negative activation energy over R. So where I'm going to find my activation energy is from this slope for a natural log of K versus 1 over temperature graph. You have to be very specific on what sort of graph you're dealing with. Now, slope is not equal to negative activation energy or activation energy. Slope is equal to negative activation energy over R. And this R value is your gas constant, but since we're dealing with energy, we use 8.31. And remember, the reason why we use this R value is because its units is joules per mole Kelvin. And anytime we're working with energy, we have to use this joule form of R. So if I know that slope is equal to this, activation energy is equal to negative R times my slope value. So that is how I calculate activation energy. Now, if you're curious, you might say, all right, well, that's cool and everything, but where in the heck are you getting all this stuff? How do you know that natural log of K needs to be here, 1 over temperature needs to be here, and the slope is equal to that? All of this stuff is derived from something known as the Arrhenius Equation. You do not have to know the Arrhenius Equation. I'm just trying to show you where it's coming from. Here's the Arrhenius equation here. It's basically a y equals mx plus b equation. So your y is natural log of k. Doesn't that look familiar? Okay. Your m is negative activation energy over r. That looks quite familiar too. And your x is 1 over temperature. That's pretty familiar. And then the y-intercept. You see your y-intercept here. You have a value. It is the natural log of k initially. And so what they give this is they say that is known as A, the Arrhenius constant. And so you would plug in an actual value for that. Now, do you have to apply Arrhenius equation for AP? No, you do not have to. I just want to show you where this is coming from. What you do have to be able to do is explain how to find activation energy. You can't just say this for your answer. You have to say, I have to collect data, temperature versus rate constant, plot natural log of k on my y-axis, 1 over temperature on my x-axis. My slope is equal to negative activation energy over r. So therefore, activation energy is equal to negative r of time slope of my natural log of k versus 1 over temperature graph. Okay? Very short and sweet. They ask this question every now and then, especially on free response. So make sure you know how to answer it. So that's all I have for kinetics. Hopefully you guys are feeling pretty good about this unit. And remind me, I will do those demos as long as you remind me and I don't forget. So I hope this is making sense, coming all together, and I'll shut up for now. So have a good day.